So I want to talk about this very common type of question that you see for angular momentum conservation problems that also gets a little bit into questions about conservation of kinetic energy. And that is this whole thing of like, you have a horizontal rod with a pivot on one end, you have like a clay ball that is projected toward it and it hits the end or some other location on the rod, and then it sticks together and it starts to spin on that axis. And this is just spinning horizontally. So in this diagram here, this is like a bird's eye view with the pivot point on the left. We see the clay ball, initial velocity, and the clay ball collides. It sticks to the horizontal rod. They rotate freely at a constant angular speed. And so to correctly answer questions about this situation, there's like three big ideas that you have to understand, and I'm going to go over those three ideas and some of the important conceptual and mathematical understandings that you need to have to like really deeply understand what's going on here, and then transfer that understanding like to multiple choice and free response types of questions. So first, we're going to talk about like focusing on the clay ball itself. Why is it, how is it that we can model the clay ball as having angular momentum or having angular velocity, and writing an expression for the rotational inertia, aka moment of inertia for the ball? Then we're going to get into how does the speed after the collision compare to the initial speed of the clay ball like beforehand. That's a momentum conservation question. And third, we'll talk a little bit about like kinetic energy. Is kinetic energy conserved during the collision? Why or why not? And where do those concepts kind of like come from, like prior understanding of topics. So let's get into here. How is it that the clay can have all these like angular things, angular momentum, moment of inertia, and an angular speed? So we can think of, here's like what I want you to kind of imagine here. At the moment, like right before the clay ball strikes the rod, we can, this is like a simplification here, but you kind of have to do this. We can kind of imagine here that there is the clay ball a distance from the pivot point. In this case, that would be equal to the entire length of the rod. That initial velocity that the clay ball has is like a tangential velocity if we were to imagine this curve that the ball is like going around. So V initial can be modeled as a tangential velocity. The distance from the clay ball to the pivot point is like our R value in the moment of inertia equation. And then the other thing that we kind of have to think about is like which moment of inertia equation fits the clay ball. And if we think about a mass that's like rotating on the end of a string, which also matches up with like a hoop because you have all the mass rotating around the outside, that model for the rotational inertia of the clay is mr squared. And again, in this example, R is equal to the length of the rod, but say you have the clay ball hitting at like half the length. You could model R as like 1/2 L being the length of the rod. So with the moment of inertia being equal to mr squared, we can also remember here that the angular speed can be written as a tangential velocity divided by R. And the angular momentum of the clay ball, angular momentum in general, is the moment of inertia times angular speed. And I'm just gonna like do a little substitution here because there's something that I want to mention about that. So if we're multiplying mr squared times that tangential velocity over R, we get that mrv equation that you may have noticed come up as like just kind of one of these specific models for angular momentum where you have this like mass rotating around. We also use that with like planetary motion and that kind of thing. We don't have sine theta there just because we imagine here this velocity vector being perpendicular to the lever arm. So sine of 90 degrees is 1, we're gonna leave that off. So this is how we model the clay ball with having a moment of inertia, an angular speed, and angular momentum. So we'll kind of like translate that then into conservation of angular momentum. So if we want to then do something like compare how the speed of the clay ball before the collision is, like what's that compared to the speed of this combined clay rod system after the collision, we want to apply momentum conservation ideas. So like I mentioned before here, we can model angular momentum for the clay itself. So anytime we're modeling like conservation of momentum, whether it's linear or angular, we have to identify our initial and final conditions. So in this case, the initial condition would be right before the impact. So the rod itself is at rest. It doesn't have anything going on before the impact. So our initial momentum for this system is the angular momentum of the clay ball all by itself. So we just looked at an equation for that. So I'm just gonna pretty much like rewrite that here. So you, in like the more simple form. So you would have the moment of inertia of the clay, you would have the angular speed of the clay initially, that gives you your initial momentum. But after the impact, now you have the rod and the clay ball moving together. So the moment of inertia would have to be the combination of the moment of inertia of the clay, moment of inertia of the rod, times this like final angular speed that they have together because they're moving together. So right off the bat here, we want to recognize that our initial angular momentum and final angular momentum are equal. Momentum is conserved. We have no net torque from some external force. We have no friction, which we know because if we have constant angular speed, it's not slowing down or anything. So if we have, I'm going to kind of combine these equations because the initial and final are equal. The clay initial conditions being equal to this combination of the two together, initially you have this lower moment of inertia, which would mean you have like a relatively high angular speed. Okay, so you have like low moment of inertia, high angular speed. But once the collision happens, that moment of inertia goes up. So to keep those sides of the equations equivalent, you're going to have a smaller angular speed after the collision. So this is lower than it was before, this is higher than it was before, because we have to keep balance on both sides of that equation. So common sense might tell you immediately that like in this collision after it occurs, their speed together is going to be slower than the speed of the clay ball by itself. But writing out this momentum conservation equation tells you exactly why. I'm just going to take it a step further just to show you how that would kind of like play out if we were to put more variables in here. So we modeled this initial momentum for the clay ball as mRV previously. And then if we're looking at this combined moment of inertia clay and the rod together, the clay, again, that's just mr squared. And the moment of inertia equation for this rod, it's uniform, is 1/3 m of the rod L squared times that angular final speed. So we could do something, for example, like solve for the angular speed and calculate what that actually is after the collision. So that is how you can apply conservation of angular momentum, actually like with the math to support this idea that your final speed post-collision is going to be smaller than your initial speed, and there's a way that you could actually calculate what that is. All right, so our last point here, let's talk a little bit about this kinetic energy being conserved. And something that I think like students can kind of miss sometimes, because it's like, oh, like we did this stuff with collisions a long time ago when we were talking about linear momentum, is that whether something is like an inelastic collision or elastic collision, that concept still applies. So the difference between an elastic collision and an inelastic collision is just that if it's elastic, kinetic energy is conserved. Your total initial kinetic energy equals your total final kinetic energy. But if you have objects that collide and stick together and move with that same final velocity, that's an inelastic. Usually we call it like a perfectly inelastic collision. And like the defining characteristic of an inelastic collision is that kinetic energy is not conserved. In either kind of collision, momentum is conserved. Like momentum is always conserved unless there's a net torque, which there's not, if we're talking about the system of the rod and the clay ball together. So in this case, your initial kinetic energy looks like the kinetic energy of the clay ball before that impact. So you have like the 1/2 mass of the clay ball times its initial velocity squared. But your final kinetic energy, we're now getting into rotational kinetic energy. So if you recall the equation for rotational kinetic energy, it's 1/2 I omega squared, where now I is your combined like clay and rod together. And that angular speed there would be the final angular speed that maybe you find that with your momentum conservation equation. And what we would find if we were to actually calculate out these two quantities is that your initial kinetic energy would be greater than your final kinetic energy because this is an inelastic collision. So some of that kinetic energy gets like lost. It's not destroyed. It's not like, that's not how kinetic energy or any kind of energy works. But in the deformation of the clay ball, you have kinetic energy being transformed into other energy types. So those are 3 big ideas here that you need to kind of know and understand when you're answering questions like this, especially if you're taking like AP Physics 1. This scenario it comes up a lot because it's a great way to model conservation of angular momentum, to ask questions about conservation of kinetic energy, to test you on can you write these expressions for moment of inertia, and can you like kind of translate this clay ball motion initially into rotational motion. So I hope that helps clear up some things for you guys. I know, like I said, this one's a little bit tricky. So if you have any other questions on this type of scenario or anything similar, leave them in the comments and I'll either answer you back, or I'm always looking for other ideas for videos to make to help you guys out. So make sure you leave a comment, subscribe if you want other videos like this, and make sure that you are paying attention for new videos coming out because we're doing a lot of rotational motion stuff right now. So I hope that helps you, and I'll see you next time.